Welcome to solverfy.
This is a simple case where we just have, I guess I forgot to put an X in here. So we have a simple mass supported by two springs and a damper. The springs have the same damping coefficient. Springs have the same stiffness. So we have mx double dot, but I guess, well, this one is hanging vertically, but maybe I'll just use x instead of y here. So mx double dot plus cx dot plus 2kx equals 0 because there's no external forcing acting on the system. So the equivalent electrical differential equation is L times the second time derivative of the charge plus R times this would be the current, and plus 2 over the capacitance times Q. Now, we could either say that we get a capacitor that has this capacitance, but actually getting a capacitor of this capacitance is actually making two capacitors in series. So one of the things that's kind of unique between electrical and mechanical circuits is electrical, the capacitance of or stiffness, if they're in series, they add up. If they're in parallel, they get 1 over the differences here. And it's just the opposite for capacitors. So these capacitors are in series. Effectively, could have put the other capacitor here and got rid of this one. So these are actually in series, where these springs are in parallel. But we can see that because the spring constant is related to 1 over the 1 over the capacitance. We can see that now this gives us twice the capacitance, two over the capacitance. Okay, so that's why we have two capacitors in series here, and the effective capacitance of this would be C over 2. But the effectively, we put that in here, we get 2 over C, 1 over that. There's no excitation here, so we just have kind of a closed circuit with nothing providing a current. So we're assuming that maybe we're given some initial charge somewhere. So maybe one of these capacitors were charged up, and then we let it go and see what it does. So we just have this loop with the inductor, a couple capacitors, and the resistor.